This is the video overview of a linear regulated power supply unit that we've studied in TAFE, New South Wales. These units were made several years ago, but they're just as good today for learning about linear regulators as what they were right back in 1980. This particular one uses a Darlington output with a 2N3055 series high-pass transistor driven by a 2N3054. The reason that we use the Darlington there, I've sort of sketched it out down here when it was done in class because these are the board notes. This transistor is actually doing all the work, so I've tried to demonstrate here that the 2N3055 is going to get quite hot. That's got a certain beta characteristic associated with it, as has the 2N3054. Might notice 5.4 and 5.5, they're sort of a pair that back in the day they were designed to go together, this one driving the more higher one here. So the overall beta that we get in this, of course, is it's a beta multiplier, so the total beta is B1 times B2. That allows us to drive the minimise the current that we need to drive the 2N3054. Otherwise, we'd need a pretty hefty sort of a transistor to be driving all that base current into the 2N3055. If this supply is going to deliver, say, 2 or 3 amps, you'd have to divide it by the beta. If it was only one transistor of about 40 or 30 or whatever it is, wouldn't be a very high beta of a power transistor like that. And that driving transistor would have to work pretty hard. So this is the way that we allow the driving transistor, which is Q3 in this case, to not have to work quite so hard to supply current into the base of Q2. In fact, the base of Q2 here is being supplied through R1, which is a 1K resistor. And if we were to sever the collector on Q3, we'd have this one pretty well turned on, you know, it'd be turned on all the time, and this one would also be turned on, and we'd have a fairly hefty flow of current being able to be pulled through this if we put a load on there, because we'd have a dynamic resistance there that was pretty well set because of that base current going through the beta multiplier. The idea of transistor 4 is actually to pull this base voltage down towards ground. And the more that we turn this transistor on, the more that we pull that base voltage and therefore base current down towards ground. So in fact, this becomes a voltage controlling transistor, and we'll see shortly it's also an error correction transistor. So we've got a voltage divider on the output of our power supply. We've got a variable potentiometer supplying the base on Q3. And as I said, the more current that we put into Q3, current, voltage here working together. So if we were to lift the wiper up towards rail, that's going to supply more base current to Q3, turn Q3 on harder, and therefore the collector voltage on Q3 will fall, which pulls the base down and drops the output voltage from the supply. There's a reference voltage here which is done just by a simple silicon diode which is forward biased. I've said here it's a little bit strange because quite often we expect to find a voltage reference which is especially in a simple series pass supply like this, a smaller Zener diode, maybe 3 or 4 volts. The reason that this has been done with a simple forward-biased silicon diode means that we can get quite a low output voltage from this supply. We're going to have 0.6 across that, 0.6 dropped across that one there, so there's 1.2, and then the 0.6 across that. So we can really get down to around about 2 volts upwards with a supply like this. Whereas if this had been done with a 6 volt Zener there, I'd have a supply that started from about 7.5 or 8 volts, you know, so that was probably the reason why this was done back in the day. Another interesting thing about this particular circuit, it's got the overcurrent sensing resistor in the negative rail. I've actually never seen that done before, so it's really quite unique. Normally we see this resistor up following the series pass transistor. and then being sensed by another BJT and feeding back into some error correction circuitry, or in this case current sensing circuitry, to start to shut down the supply and protect the pass transistors. So it's a 0.68 ohm, 680 milliohm resistor, and if you run the maths on that, it appears that we've got to turn on a transistor. Well, we've got two transistors here to turn on. In fact, Q5, this is silicon, Q5 turns on, of course, with around about 0.6 volts between the base and the emitter. So when we drop 0.6 of a volt across that resistor, we will be able to turn on Q5, collector will go low, 1500 ohm current limiting resistor. D2 is an LED, which is at the end of the supply over here, and that light will illuminate. This is purely an indication stream up through here to let the operator know that, we've started drawing excessive current from the output of our supply, and this is sensing that we have in fact taken excessive current. The maths I've done here, 0.6 volts, of course, is what we need to turn the transistor on, divided by the value of the resistor. 882 milliamps is the point at which the supply starts to fold back. But hey, this particular Q5, R3, D2 stream is only for indication, overcurrent indication transistor. Q4 is the one which is actually doing the folding back. And if you look at Q4, we've got the emitter going to the same point in the circuit as Q5, and the base goes to the same point in the circuit as Q5. But the collector path here goes up through a 1K to rail. We've already looked at that. That's the same resistor that supplies the base current to Q2, Q1, Darlington pair. And also it's supplying the collector voltage and collector current down into Q3. Well, in this case, if this transistor turns on Q4, it's sharing R1 as well. It will cause R1 to draw a lot of current, because this is going to turn on, the more current you draw through the supply, R6 gets a bigger voltage drop across it, turns on Q4 harder. Q4 starts to draw a lot of current, pulls this voltage down. That has the effect of lowering the output voltage from the supply. We call that folding back. If we've lowered the output voltage from the supply, we've also lowered the amount of current that the supply can deliver. So these two transistors work together, and I'll say more about that shortly, because it's a bit strange how they've done it, and it doesn't work quite as well as what the designer originally intended it to, I do think, because of the differing characteristics of the two transistors that he's chosen to use. What else have we got? D1. D1 is it's another weird thing in this supply. It's used to provide reverse polarity protection to the supply, and in so doing, you're losing about 0.6, 0.7, maybe even 0.8 volts across it, because with a diode, silicon diode, the more current that you draw through it, the more you lose as a voltage drop across it. I've got a bit of a graph that I'll just scroll down to at the bottom of the notes here. This is for a silicon diode, and if we look at this, you can see on the graph here that I've got, I might just change the color, and I think we should probably write silicon on here. Silicon. So the more current that we push through, here's current on the y-axis, the more current that we push through our silicon device, this is the turn-on characteristic curve, the more voltage that we drop across the device. So the device starts to turn on, you can see here, at around just past 0.5 volts in this graph that I've plotted. And then, by the time that we're up to about 50 milliamps, 50 microamps, I should say, the thing went up to about 700 millivolts, more than 700 millivolts. So we increased the forward voltage drop from 500 millivolts to 700 millivolts across the diode. So you can imagine, if you've got that's a small signal diode, you can imagine if you've got a power diode in the circuit, the more current that you're going to draw through this, the more voltage drop you're going to have across it, and that's going to cause losses in the circuit, and that's really undesirable. There's a better way to provide reverse polarity protection, and that's by using a fuse with a reversed diode in shunt after the fuse. So if there is reverse current put in, the fuse will blow and protect the rest of the circuit. But you won't get any voltage loss, except for across the fuse, and I'll show that in part 2 of this video, where I look at the voltage drop that I actually get across this critter here, which is a fuse. And that's a trap for young players. I think at 1.5 amps out, I got about 400 millivolts loss across that small fuse, little 1 amp fuse there, glass fuse, and quite lossy because of the resistance, the small resistor, larger resistance, I should say, of the small wire that goes through the fuse as its fusible element. The meter, we've got a meter trim resistor here, a small preset resistor on the inside on the panel, and the meter is calibrated in volts. And in the second video that I do here, I'm using a very low value resistor for the load because I really wanted to load this thing down quite severely and get it to go into overcurrent. The supply that we're putting into this ideally would have been an unregulated power supply, so I've used a centre tap full wave rectifier here with 1,000 microfarads across it. Of course, with very low current, showing, with 1 k ohm across this, handful of milliamps out, I'm going to have no ripple. But the more current that I draw, if I put a lower value of load on there, lower value of load resistor on there, so therefore a higher load, I'll start to get pretty significant ripple here. Normally with a Zener diode, of course, this is what we'd be seeing in our voltage reference at this point here. Voltage reference to set Q3 emitter. But in the circuit that we've actually got here, we've got 4.7K with a simple silicon diode. And why not? It's a nice 0.6 reference. I used iCircuit and I ran some figures on that. I made this up quickly, 4.7K, 15 volts. I ran it from 15 volts up to about 10, 20, 30 volts, something like that. I think I saw over here. Supply varied from 10 to 30 volts. The change was in the order of just a few tens of millivolts. So we went from, I think, about 661 millivolts at 15 volts up to about 680 millivolts at 30 volts of supply coming in, and, given that we've got current going through that diode. So over quite a wide range of input voltages, that holds its value pretty steadily. There's a few different types of transistors in this circuit. We're using a BD139 at one point, and in fact, before I pulled the supply apart, I thought that the BD139 would have been this resistor here, and I've written that on there, but that was in fact wrong. That is a BC108, and I think that might have been a design flaw in this circuit, as I'll show you shortly in the second video, and towards the end of these notes as well. Output voltage setting, bit strange this. You'd expect that as you put the wiper up that you get more voltage out. No, as I said before, if you increase that wiper up towards rail, you're actually getting more voltage, more current going through Q3, turning on Q3 more, pulling the base of Q2 down, turning Q2, Q1 combination off, getting a bigger dynamic resistor across there, and dropping the output voltage down lower. And here's just a more simple supply. If we always think about this as our reference, just a simple series pass, dynamic resistance, a series resistor supplying current into a Zener diode. The transistor base is sharing that current. So providing we keep that Zener diode within IZK and IZ max, we're going to have a nice constant voltage across that Zener diode. Is it possible to lift that from 10 volts? Of course it is. We could put that to 10.6 by putting a silicon diode on top of that. And that's a different story again, because there are differences that we see in diode characteristics. Another circuit from our textbook here in the notes, this one a little bit simpler again. There's no current foldback in this particular circuit. We've only got one control element. This is voltage control and its error correction. Now, I said that our transistor here provides two things in the circuit. This is a voltage control and its error correction. Let's see how that error correction works. If the output load becomes a smaller resistance and it draws more current, the voltage at Q1 emitter is going to be seen to fall. If that falls, all the voltages down this voltage divider, and therefore the wiper on RV1, that voltage is going to fall as well. If that falls, we've got less current going through Q2. Q2 turns off, the collector voltage rises, therefore more current is available to go into Q1. The base voltage has risen in comparison with the emitter, and therefore you get more current at the output, more voltage at the output. So this is a closed loop control system. This pot, we can adjust the voltage, and we can also rely on this circuit for error correction to maintain the output voltage quite stable. Now, looking underneath the board, I'll show in the second video that some of these boards are quite hard to look underneath, and LED lights are a real luxury these days, because just putting a nice big LED torch onto one side there, I've been able to make quite a nice photograph to draw on and show me all of the foils, copper foils on the board there, so that I could work out what was going to what. Said there that this board was made back in about 1980, and that was the year after Mount Druitt College was electronics department was opened. Look, with a board such as this, it was really impossible to trace the foil for the circuit without lots of light underneath the fiberglass. This was accomplished by using a LED torch. So then I've just gone back to the main circuit and I've transcribed the information that I needed to have onto the board. As I said earlier, I really did think before I pulled this apart that the BD139 would have been used for Q3, which is the error correction and voltage setting transistor. But in fact, no, they used a BC108 for that, quite a small signal transistor, and they've used a BC108 to drive the LED for current, to show that you've gone into current dropout or current foldback. And Q4 here, they used the BD139 to actually do the folding back. So if we just go back up to the circuit again and we look at Q4, they used the BD139 there, and that must have given them some real headaches, because the beta of the BD139 is only about 30. The beta of a BC108 is about 400. This thing drew a stack of base current, and that would have really messed up the sensing that was happening between these two transistors. So what they've done, when I went through the circuit, I found a little mystery package over here. I found another diode which is not shown in the original circuit diagram. And what they had to do, I've made some notes here about that. They had to lift the base turn-on, the turn-on voltage for this transistor, by putting another 0.6 volt silicon diode in there. They've lifted the turn-on voltage to about 1.2 volts. So they'll get the indicator light come on first, and then they'll get the actual current foldback starting to happen later on. I did short circuit that to put it back to how the designer had drawn the circuit, and what happened, the foldback happened too early, and the current limiting light did not come on at all. So the BC108 Q5, all of its base current was being stolen, if you like, by this transistor, and that was never getting to turn on. And I've sort of discussed that in these notes here, and I've shown the BC108, you've got a beta of around about 400, and the BD139, look, minimum 40, it could be 40, maximum 160. You know, I'm probably being generous by saying it's 100, but even if it was 100, that's going to be a quarter of the other transistor, so this one's going to be a current thief. And if we have a look over here at the IB1 and IB2, we form a current divider from those two transistors. They would have been ideally identical transistors, like both BC108s. And this transistor here which is doing the work all the time, should have been the BD139, I would have thought. This transistor is not doing any work, neither is that one, until we get into current foldback. So there was no reason why they couldn't have both been BC108s. This transistor, on the other hand, he's got a lot of current going down through him all the time, depending on where the output voltage is set. If this wiper goes up to the top of the resistance there and turns this transistor on hard to drop the output voltage down to about 2 volts, this transistor then has current flowing through it all the time, and touching that transistor, it was quite warm. It was probably running at about 50 degrees Celsius at low voltage. So I really think that there was a design problem with this particular circuit. And there again, we can even think about that current division and about the different turn-on points with our silicon diodes. And especially if you have two mismatched diodes, if you've got the BC108 and the BD139, which in the circuit, they really do look like they're running as a differential pair, but they're not. They're just sharing. They're sharing the same input path, taking a sample across R6 of the voltage, but one is just supplying an output LED and one is actually turning off this transistor. I made in those notes, I think that's a very poor design. You're relying on one transistor to do one thing and one transistor to do the other, but the two transistors are not talking to each other, so they're happening totally independently. Would have been far better, I said down here, to do that with a proper differential amplifier. Where did I put that? Yeah, having one standalone transistor for the overcurrent indicator LED has proven to be a problem in the circuit as it stands. The two base currents have different current paths. I think I said there somewhere, some sort of an op-amp comparator would have been a far better design model, even a true differential amplifier on the same die, and then the output amplified to give enough current to cause a significant voltage drop at the base of the pass transistor. So one device, therefore giving us the indication and proving that we have got foldback. Because this thing in the worst possible case could tell us that we've got foldback by the light coming on and the foldback transistor never actually turning on to give us the foldback. And if we take that extra diode out, we get a massive amount of foldback and the indicator light never comes on. So that was a bit of a flaw in the circuit, and I'll show that in the second video. All right, this has been Greg Moore for TAFE New South Wales, and that pretty well wraps up the first video about this particular voltage-controlled and error correction series pass linear power supply. Thank you.
My dear, and are as old as I. You'll often ponder on the years that roll so swiftly by, my dear, that